My name is Gary Pocock, and this is my Week 5 reflection for the Physics Modelling Instruction course. This week I'm going to talk about three things. Firstly, I'll mention the bleachers activity that we discussed in class. And secondly, I'll very briefly talk about the mapping electric potential activity. But then I'll spend most of the time reflecting on the difficult concepts of field and potential. Alright, first up, the bleachers activity, which I really liked. I thought that was a very good physical activity for developing the concept of electric potential. So what I was thinking about was, once the basic concepts have been established, how we could follow that activity up. And a couple of things I thought of was, at my workplace we've got some steps and we have a wheelchair ramp beside the steps, but the gradient on the ramp is much lower than the steps, so the ramp extends much further out. So it'd just be interesting to have students some standing on the steps, some standing on the wheelchair ramp, and asking at what points do they have the same potential, just to convey the idea that it's the vertical displacement that is a crucial thing for gravitational potential, not the horizontal. We've also got some steps, a small set of steps, and then a long flat area, then another small set of steps, and these are quite visible to one another. So I thought also I could have students standing on various points on these steps, and an obvious question here would be, where should the zero go? And some people might think it intuitive to place it at the bottom of the lower set of steps. Some people might place it at the flat area in the middle, and just they could discuss that idea and realize that it really is quite arbitrary and something that is chosen purely for convenience. And finally, just mention an analogy that I think Don raised in our breakout group on this, and he just said, imagine a slippery dip, so a slide, and so he drew a slide, and then at a point at the top of the slide, that is a point of gravitational potential, and then you show the slide again, but this time you have a child sitting at the top, and you can say, well, now the child has energy, but without the child there is no potential energy, there is only gravitational potential. I thought that was nice. It's simple, and it vividly conveys the difference between potential and potential energy. Okay, moving on. Now the 3D potential plot, I wasn't actually able to do that because I didn't have the equipment. I did play with the spreadsheet, and I found that very good, surprisingly easy to use. I could see there would be traps for students, but overall I didn't have any problems generating 3D plots with it. So it's definitely something that I would like to do, like to get the equipment for, so that I can do with my students. The only reflection I had on it was that 3D plots are notoriously difficult for students to interpret, so I really thought that having some guiding questions to accompany the plots would be very helpful, so that we can ensure students do understand what they are looking at when the 3D plot is generated. Alright, now on to something that I've been really thinking hard about all week, and it's such a difficult topic, and I guess this is why physics is so fascinating and physics teaching is so fascinating. It's because you come up against deep and difficult concepts right in the very first courses of physics, and fields and potential are two such concepts. So I went searching around to see what I could find, and one thing I came up with was a paper by Roche, written quite a while ago. The actual title of the paper is Applying the History of Electricity in the Classroom, a Reconstruction of the Concept of Potential. So he focuses most of his paper on the concept of potential. I think I might leave potential until my next reflection. I think I'll run out of time, so I'm going to focus mainly on the field concept in this reflection. But a couple of his introductory comments grabbed my attention, and this one, where he says that he feels that verbal explanation has been neglected, or at least not developed to the same extent as mathematical and experimental representations in physics. I don't know about neglected, I don't think that's quite right, but I think it's reasonable to say that it is certainly true that mathematical, especially mathematical presentations, have outstripped our ability to provide satisfactory verbal explanations. And he goes on to say that physics is particularly difficult to explain rigorously and clearly, and we need to develop special explanatory concepts to match the complexity of the subject. And he suggests in the last sentence that such concepts can be developed not simply by abstract reasoning, but also in the context of the effort to explain physics clearly in class. And I really like that, because I think that really connects up with what we're trying to do, especially in modeling instruction. So pushing really hard to try and get as clear as we can on the abstract concepts. And it reminds me of Feynman's dictum that he never really understood something unless he could write a first-year introductory lecture on the topic. Or Feynman used to say, we don't understand it, meaning the whole physics community doesn't understand it unless someone can write a first-year lecture on it. Okay, so now let's apply these ideas, thinking clearly and deeply about the field concept. And when I think about how I try to explain it in class, one of the first things I always do, of course, is to explain why this concept was felt to be necessary. Because there was a problem with the idea that forces could act over a distance with no intervening medium. But I realize when I say that is really not a felt problem for students. Students have been playing with these, they're used to static electricity, they see things attracting across space. So when I say, action at a distance is a real problem, and the physicists really need to find something that fills the space in between, I don't think they articulate it very well, but I can see on their faces they're going, well, why? And that's really challenging, because you have to actually situate yourself back into the beginning of modern science in the 17th century, where the philosophy of mechanism was on the rise, and to really appreciate why those early natural philosophers felt so strongly that action at a distance should be avoided, and their feeling that they needed to get away from explanations that were to them magical. And the only thing I could think of was to try and convey that was to actually tell the students a little bit of the history itself. Now, I love the history of physics, and I like to slip it in to my classes when I can, but I feel you need to do that fairly judiciously, not overdo it, but nevertheless to convey that there was a genuine struggle by the very best physicists of the day how to solve this problem, and why action at a distance was a problem, and why the mechanical philosophy was held to be the way to make progress in science, as we would now call it. So I'm still struggling at that one, how to make it vivid that action at a distance is a genuine problem for which we need the field concept to solve. The other difficulty with the field concept is the tension between just a mathematical approach and a physical approach. And this goes right back to, well, definitely to Newton himself, when he proposed his law of gravitation. He knew full well that this was an action at a distance law, and that he was going to be criticized for that, which he was. And that is indeed the reason why he put the word Mathematica in the title of his book, Principia, because that was how he responded to this criticism, that he was giving a mathematical account, not a physical account. And it seems clear from what Newton said that he fully agreed that his account was incomplete and that there needed to be a causal explanation for how gravity was able to extend across space. And when we come to Faraday and Maxwell, we see that same tension between a purely mathematical or purely modeling account and physical reality of fields. So this paper talking about the origins of the field concept, and he says here how tentative Faraday and Maxwell were, initially at least, about the physical existence of the field, and the realization, especially by Maxwell, that straightforward mechanical analogies were almost certainly not to be trusted ontologically. In other words, we couldn't explain the field in terms of any physical concepts that we were familiar with. And I like this last sentence here where it said, if it has not been for Faraday's stubborn persistence in seeking arguments for the physical existence of ontologically odd but arguably real forms of electric and magnetic action, the notion of a field might have been appreciably longer in coming. Okay, so how do we sum all this up, and how do we help our students understand the concept of field? Well, there's no clear-cut answer, but it looks what we have to do is use every single analogy that can come to that we can think of to try and convey the idea. So I really like, for example, Matt's little dialogue that he explained last lesson, where he asked the student, where you ask the student, does the field exist here? And if they say yes, and you say, well, prove it, show me. And of course then they have to pull out a test mass or a test charge. Now of course that doesn't prove the existence of a field, but it certainly makes the idea very plausible. And using history to convey the struggle for developing the field concept, I think that's telling a story. I think that's very helpful as well. Ultimately though, I come back to the point made in this Feynman video down here, that fields are absolutely fundamental. We explain everything else in terms of fields. So we cannot say what a field is without indulging in circular arguments. For example, the rubber band analogy, which is very useful for conveying the key idea that energy is stored in a field. That is obviously ultimately circular because the forces in a rubber band are electrical and magnetic forces themselves. But nevertheless, if we keep acknowledging the limitations of our analogies, the analogies are still very helpful.